Hello, welcome back to AE 3530, System Dynamics and Vibrations. In this video, we are going to go through work, energy, and power. So if force is considered to be a measure of effort, then work is a measure of accomplishment. And the energy is then the ability to do work or to accomplish something. We're not going to go through too many derivations in this section so you're going to want to go read section 1.3 in Meyerowitz for those derivations. So kinetic energy is the energy associated with motion, and it can only be stored in inertial elements. It's a conservative energy associated with motion. In vector form for translation, the kinetic energy T is equal to 1/2 m times r dotted with itself. So the kinetic energy is a scalar, and it results from a dot product of the velocity vectors. You can also go and define this for rotational systems. We're going to skip that here. Potential energy is an energy that is stored by some conservative element. That could be springs or gravity or any other kind of conservative element. For gravity, we'll always want to define a position of zero potential energy, and then we'll be considering the change in potential energy as an object moves. If we choose that position of zero potential energy to be at a height of 0, then we can write the potential energy to be equal to mgh for just a standard system where h is the height. Now for something like a pendulum, this height is going to depend on the angle of rotation, and it will become a little bit more complicated in general. Now for springs, the general form is going to be that the potential energy is equal to 1/2 k times x squared. And we'll talk about what it looks like for a nonlinear spring. Or if we're thinking about change in potential energy at, let's say, two different points in time, this will be equal to 1/2 k x at time 2, that's x squared at time 2, minus 1/2 k x squared at time 1. And that is our change in potential energy. For torsional springs, it's going to follow a similar form, except that we're going to use theta instead. So we'll get 1/2 kt theta squared, or change in potential energy, delta V. We can write this as equal to 1/2 kt times theta and that's theta squared at T2 minus theta squared at T1. For some type of nonlinear polynomial spring, let's just say that the force is equal to a coefficient alpha times x to the power beta. Beta does not necessarily have to be, or in fact it does need to be an integer in the form given here. There is a way to write this where beta doesn't have to be an integer. For now, we're just going to assume it's an integer and not worry about what to do when it's not an integer. In this case, the potential energy is going to be equal to this alpha divided by beta plus 1 times x to the beta plus 1. And to give you an example, if we have a spring that is dependent on the displacement cubed, so let's say F is equal to alpha x cubed, the potential energy will be equal to 1/4 times alpha times x to the 4th, or for the change in potential energy, we will get here 1/4 alpha times x to the 4th at time 2 minus x to the 4th at time 1. We're often going to choose our reference potential energy to be at static equilibrium, where the displacements are 0, and therefore we can neglect this second term in that change in potential, and only include x to the 4th, or x squared. Okay, so the work done by a force is defined as the work done from time 1 to 2 is going to be equal to the integral, or from position 1 to 2, we're going to integrate from position 1, r1, to position 2, r2, of f dotted with dr, and we can expand this and do an integral from time 1 to time 2 is equal to f dotted with dr dt times dt, which then is going to be equal to the integral from t1 to t2 of f dotted with r dot dt. And so in other words, the work done by a force from 1 to 2 is going to be equal to the integral from t1 to t2 of the force dotted with the velocity vector integrated with respect to time. Okay. So note, you can use this integral form to compute the potential energy of a conservative element or the energy dissipated by a non-conservative force. And we're going to deal with that in a moment. So that being said, you can find the potential energy for a nonlinear spring, for a linear spring, or any other kind of conservative force. You can use this integral to find the work done or the potential energy of that. We're not going to talk about what dampers do. We mentioned previously that dampers convert mechanical energy into heat and therefore dissipate that energy. We're going to find that dissipated energy by computing the work done by the damper. So keep in mind that typically force from a damper is equal to, generally it's going to be equal to minus c times x dot. When you account for the fact that the force due to a damper opposes the direction of motion always, meaning that if x is positive, the force is going to point in the negative direction. If x dot is negative, if it's moving in the negative direction, then the force is going to point in the positive direction to oppose that motion. So then we can write that the dissipated energy, we'll call this dE, and we go 1 to 2. This is equal to the integral from t1 to t2 of x dot minus x dot. So in fact, let's pull this integral. We're going to pull the minus sign out. We'll have minus x dot times f dt equal to, we're going to plug in for our force. In fact, actually, at this point, we should leave that negative sign out. That's my mistake because it's stored in the f. So in this case, we'll have integral from t1 to t2 x dot times minus c x dot dt. Pull the minus sign out. We'll get integral from t1 t2. In fact, we can pull out c because it's a constant. So we'll have minus c times the integral from t1 to t2 x dot squared dt. Okay, so then the dissipated energy, dE 1 to 2, is equal to minus c times the integral t1 t2 x dot squared dt. Or this is the work done by that force, which is equivalent to the dissipated energy. Now, this integral is one that we, as a species, we do not know how to solve. We know that a solution does exist to this. We do not know what that solution is. And so the best that we can do is to compute this numerically. Typically, we normally do a numerical integration. Okay, the mechanical energy is what we're going to define to be the sum of the kinetic and the potential energies, whereas the total energy is going to include the dissipated energy as well. We're going to use E for the mechanical energy, and we'll define that the mechanical energy E is equal to the kinetic energy T plus the potential energy V. So when there are only conservative forces acting on a system, the mechanical energy is going to be constant, and it will be equal to the total energy in the system. So in this case, E will be equal to a constant. And what that means is that the mechanical energy at one point in time, let's say T1 plus V1, is equal to the mechanical energy at a different time, let's say T sub 2 plus V sub 2. Oops, let me redo that, V. Or the energy at time 1 is equal to the energy at time 2, mechanical energy, that is. When we have both conservative and non-conservative forces, but no external forces acting on a system, the mechanical energy is going to decrease with time. That's due to the dissipation that's occurring from the non-conservative force. But the total energy is going to be a constant. So we computed the work done by a damper above. If we come here and we say, conservation of energy says that energy is equal to the work done, we will have T plus V is equal to the minus, we'll just say minus dE here. And then what we'll find in fact, let's actually rewrite this. We're going to write this as the change in mechanical energy, E2 minus E1, is going to be equal to minus dE1 to 2. That's the work done by the dissipation or the non-conservative force. And what we'll find if we bring that over to the other side is that E2 minus E1 plus dE1 to 2, this is going to be equal to a constant. Okay, I want to just make a clarification here. We put a negative sign here. What we should really do is, instead of saying this is dE, we should actually call this the work by the damper, let's say. And let's come and change it here as well. The work by the damper from 1 to 2. And then we'll write here that the dissipated energy from 1 to 2 is equal to the negative of the work by that damper from 1 to 2. Such that here we would have, if we come back and make a modification here, we would have the work done by the damper from 1 to 2, which will be equal to minus the dissipated energy from 1 to 2. And then we can bring it on over. And now this is all true. Now this is then equal to a constant. The change in mechanical energy plus the dissipated energy will be equal to a constant. When both conservative and non-conservative forces, including external forces, act on the system, the mechanical or the total energy changes is equal to the work done by the external forces. So in this case, we'll say here that E2, mechanical energy at time 2 minus mechanical energy at time 1, plus that dissipated energy from 1 to 2, this will be equal to the work done by any external forces from 1 to 2. Generally, we're going to consider the E1 or the mechanical energy at time 1 to be the mechanical energy at t equals 0, and this will be the initial state of the system. So something we'll talk now about is power, and power is just the time rate of work. That means that power is the time derivative of the work done by a force, so P will equal dW over dt, or in other words, the power is equal to the force dotted with the velocity. You can see that when we computed the work done by a force, we ended up having inside the integral the term power here. So we're going to come here and we're going to put here that this is the power of the force. So the work done is the time integral of the power of the force. So we can compute the mechanical power and then integrate that to find the work done by that force. Okay, in the next video, we're going to go through an energy method for deriving equations of motion for single degree of freedom systems.